Yeah, um, so welcome to our lecture today on Saturday. It's a I realize you must be completely burned out on learning anything new, but so today I will talk about classification methods, and I really will take you from the beginner's level to hopefully the state of the art. So I will talk about methods that have been published in the 1930s, and then I will describe methods that have been described in 2013, meaning this year. So first we start out with supervised learning, which is also known as prediction analysis or yeah, prognostication and so on. So to give you a motivational example, consider tumor classification. Of course, when you have a tumor, the precise classification is crucial for informing your treatments. And current methods classify these human malignancies based on so-called morphological criteria. In other words, a pathologist looks through the microscope. And but this is a rather crude measure. And so the hope was that we can use genomic data to arrive at a more reliable tumor classification, which then informs treatment decisions. And when it comes to tumor classification with gene expression data, there are really three main types of statistical problems. The first problem is to identify new or unknown tumor classes. And imagine you have a tumor, and under the microscope, these tumors all look the same. However, they could really fall into two distinct classes when you look at them in a molecular way. And to accomplish that, that classification, we use a clustering algorithm to group subjects into clusters. Clustering is also often referred to as unsupervised learning. It's an unsupervised learning technique. But sometimes you have a different statistical task, which is you want to classify malignancies into known classes, for example, high risk versus low risk tumor. And this is then referred to as supervised learning or discrimination or classification. Now, you hear the word supervised, and who is the supervisor, by the way? So the supervisor is really the clinical outcome, or the class. So when you have known classes, high-risk tumor, low-risk tumor, for example, then this class outcome is the supervisor. In any event, the third task that is associated with these problems is to identify so-called marker genes that characterize different tumor classes. Right? It would be good to have a gene that if the gene is overexpressed in a tumor, okay, this is a high-risk tumor, And so identifying these marker genes is also known as feature selection or variable selection. Feature is another word of variable, is another word of covariate, so it all means the same thing. And there are also many terms for describing prediction methods. There's the one term I mentioned, prediction method, then classifier, discriminator, prognosticator, supervised learning, and then also regression techniques are also prediction methods. So the reason why we have so many terms is that different communities use their own terminology. In statistics, we often talk about regression models, whereas in computer science, people would talk about supervised learning. That's the term there. All right. So as I mentioned, when it comes to these machine learning tasks, we basically divide them between unsupervised methods and supervised methods. And when you have an unsupervised method, then you assume that the classes are not known. Instead, you want to learn the classes, and the classes could be learned, for example, using a clustering method. In other words, the clusters will become the classes. And as I said, in the supervised situation, the classes are known. There's an outcome. And so then what you want to do is you want to train a prediction method in order to arrive at predictions on new data and on future observations. So when we want to carry out prediction, we assume that we have several objects. So for example, an object could be a human subject. And for each object, there's a class label, for example, a response. And the class labels could be labels 1, 2, 3, and so on. Or they could be just two classes, low risk, high risk cancer. Or it could be, their response could be disease status or case control status. Now that's, the outcome Y is, as I mentioned, the supervisor in the analysis. But also we assume, of course, that we have so-called features. In our case, these could be gene expression profiles. For example, if you have a microarray, you could have 50,000 probes. But of course, all of these statements also apply to RNA-seq data. You could have RPKMs. And so the aim is to predict the outcome Y based on the measured features. For example, these 50,000 gene expression values. So classifiers, which, by the way, where does the term classifier come from? It assumes a class outcome, meaning there are these 1, 2, or 3 or more classes. And the classifiers partition your feature space into different regions. Let me try to give you an intuitive geometric interpretation. So let's assume we consider 3 different types of irises. By the way, the iris is a flower. And when it comes to the flower, there are you can distinguish them by 2 variables called sepal length and sepal width. In other words, they measure 2 things on each flower, okay? The sepal length and width. So how do we encode this problem? Well, each type of iris is a different class. So class 1, 2, and 3. And the feature vectors, there are only 2 feature vectors. But the advantage of having only 2 feature vectors is that we can visualize it in the Euclidean plane. And so here I visualize the data. So the x-axis shows the sepal length, the y-axis the sepal width. And you notice there are these dots. Now each dot corresponds to a flower. And the dots are colored according to the type of flower we're dealing with. So say class number 1 is colored in red. So you have these red dots. Class number 2 is colored in blue, so we have these blue dots, and the 3rd class is colored in green, so they're green dots, although you can barely see them. All right. Now, when you have a classification algorithm, then it really partitions these the plane into regions. For example, here we have a linear discriminant analysis, And what you notice there are these lines that partition different regions. And how would we then classify a new flower? So imagine somebody comes with a new flower to you and says, I actually don't know what kind of iris it is, but what I know is the sepal length and the sepal width. Well, in this case, you would just see, well, in which region does the new observation fall? And let's say the sepal length and the sepal width mean that it falls into this blue region. Then you say, okay, this is a blue iris, you know. So that's how the prediction works. So this hopefully visualizes what I mentioned here, that a classifier partitions this space of the feature space into these different regions, which are here denoted as A1 through AK. All right, let me give you some additional terminology. So often, of course, we need to fit the classifier, or we need to teach it how to make predictions. And to do that, we need to have a learning set. So that's your first data set. And I distinguish the learning set from the test set, because the test set is an independent data set. Now, the learning set may be comprised of 100 different irises, for example. And so each observation comes with the measurements of the features and a class outcome, meaning this Y. And so then a classifier really maps this feature space into these K categories. And as I mentioned, to make a prediction, you ask, well, is this feature, the observed feature vector, in one of these regions, for example, AK? If it is in AK, you classify it as outcome K. You know? All right. So coming back to this figure with the iris example, when you carefully look, you notice that there are some blue dots in the green region, and also there's a red dot in the green region. So what is the interpretation of that? Well, these are observations in the learning set that are misclassified, you know, because your predictor partitioned this space into regions, and it used, of course, an algorithm to do it in an optimal fashion, but it just turns out that some irises are misclassified. They don't behave as they should, okay? And when you look at it, you could say, well, maybe having these straight lines, these hyperplanes to partition the space is too rigid. Maybe I need a smooth or a curvilinear relationship. And that's exactly what different prediction methods do. Prediction methods differ according to how they partition this space into regions. For example, there's a method called quadratic discriminant analysis, and it allows for quadratic relationships or dividing lines. So now you see, well, if you have this flexibility, the green region is bounded by a quadratic curve. There are other prediction methods which are known as nearest neighbor classifiers, and I will describe them to you shortly. But they partition the space in much more complicated regions. The nearest neighbor classifier has a parameter called K from K nearest neighbor. So K is the number of nearest neighbors. And if K is equal to 1, you get this really complicated division. However, if you have K equal to 5, it's smoother. And if you have K equal to 50, suddenly you almost get straight hyperplanes again, you know. All right. Another classification method that I will describe to you today is called classification tree approach. And so this classification tree approach also divides the space, but notice it does it by forming dividing lines that are parallel to either the x-axis or the y-axis, right? So you either cut it here, then here, and so on. So I hope I've convinced you that classification has a nice geometric interpretation. It's really all about how you partition a space. Assume again we have gene expression data, let's say 50,000 transcripts, then we are dealing with a 50,000 dimensional space, and classification really amounts to partitioning this very high dimensional space into different regions. Now, classification can also be interpreted as decision theory. There's a whole field in statistics. And in decision theory, we define probabilities. So let's say P1 of X is the probability that you observe your expression data assuming that these features come from class 1, for example, a diseased individual. More generally, pk of X is the probability that you observed your gene expression data from assuming that the person is in class K. And then, when you have these class probabilities, then you can arrive at a classification by simply maximizing them using the maximum likelihood approach, right? So let's say I have the gene expression data from a cancer subject, and then I need to decide, are they a high-risk patient or a low-risk patient? Then what I do is I calculate the probability of observing the gene expression data assuming that they are a high-risk person. And let's say the probability is 0.8. Similarly, then, the probability of observing these gene expression data, assuming that they are a low-risk patient, is 0.2. So then what would be my prediction? Well, I would say I classify them as a high-risk person because that maximizes the probability or the likelihood. Okay? So if you have these P of K of X's, these class probabilities, you really know how to classify a subject. The problem, of course, is that this is hard to calculate, these class probabilities. And therefore we make assumptions. So if you assume that you can assume that these class probabilities follow a normal distribution. Okay, so characterized by a mean and a variance vector. Of course, if you have 50,000 probes, then you have a very normal distribution with a mean vector of 50,000 entries and a matrix 50,000 times 50,000. You know, but in any event, so you would then estimate the mu and the sigma, and therefore you can estimate the class probabilities, and then you can just use the maximum likelihood approach. And that results then in a classifier, which has a famous name, quadratic discriminant analysis. Now, the only thing you have to do to implement it, you have to estimate the means and the variance, and you can, of course, do that in a fairly straightforward fashion using standard statistical formulas. And as I mentioned, that's the result we would get if we apply quadratic discriminant analysis here in the iris example. Now, one problem is that often we don't have enough observations to estimate this variance-covariance matrix, and for each class separately. And therefore, people often make the assumption that the variance-covariance matrices for each class are the same. right? Sigma k doesn't really depend on k. And if you assume that, then you come to the situation of linear discriminant analysis. And linear discriminant analysis has the feature that you get straight linear hyperplanes. There's no curvy linear relationship. But sometimes people make yet a more restrictive assumption, which is they assume that not only are all the matrices, the variance covariance matrices the same, but further that they are diagonal. They, in other words, they assume the genes are uncorrelated, you know, which in the context of gene expression data is a crazy assumption, right? Because we know genes are highly correlated. Now, although this is a crazy assumption, it turns out that the resulting predictor that makes that assumption is actually often far better than the other predictors I mentioned. Certainly much better than quadratic discriminant analysis and often better than linear discriminant analysis. So again, the predictor that makes this very restrictive assumption that they're only diagonal elements, that predictor deserves its own name, which is diagonal linear discriminant analysis, DLDA, but it also has another name which is called gene voting in the context of gene expression data. All right, so yes, so here's linear discriminant analysis. That's the slide we started out with, you know. All right, now these are all methods that were developed by Fisher, this statistician Fisher, who you know from Fisher's exact test and so on. So this is an ancient method, you know, but it works fairly well. Now I describe another very well-known method known as nearest neighbor classification. And this is a very intuitive method. So while some of you have probably got lost with linear discriminant analysis, this is a method that you can understand, so please wake up again, you know. All right, let me explain k-nearest neighbor classification. So it's really based on classifying a subject according to the subject that is closest to it, you know. Let me come up with an example. Imagine you want to take a class in the fall semester, let's say Economics 101, but you are a little bit worried about what grade you will get. Now, statistically speaking, you are dealing with a prediction task. You need to predict your grade in that class 6 months down the road. And, well, how would you arrive at a prediction? Well, one approach would be to say, well, who took this class last year? And let's say you know 10 different people who took it. And then you say, oh, you know what? My background and my educational background is very similar to that of John. And John got an A. And then you say, well, then I will also get an A, you know? And what did you just do? You picked the person who matches you most closely in a certain way that has the smallest distance to you. You used their outcome to make your prediction. So that analysis would be called one nearest neighbor analysis because you only looked at one person, you know. Assume you say, well, I don't trust the analysis. I look at the 3 people that are closest to me. So there are 3 former pupils, and then you say, well, 2 of them got an A, 1 got a B, and then you say, well, I average the results. I vote, it's a vote for A, you know. And so k-nearest neighbor prediction does exactly what I outlined. It uses, let's say, 3 or 5 people, and then lets these 5 nearest neighbors of you vote on the outcome, and you just take the outcome that gets the most votes, you know. Now, this method is very intuitive and simple, But it's unbelievably accurate, you know. It's one of the best predictors we have in terms of accuracy. A problem is that, somehow it's not widely used in genomic applications. And what's the problem? Because you need to have a learning set that is in certain ways fixed, right? Let's say you must have access to 100 cancer subjects, you know, and then when a new subject comes in, you form distances, right? And then you form the closest neighbors. And so you really, in order to do that, you need to have the whole data set readily available to form distances. So it's actually fairly hard to publish. Compare this to linear discriminant analysis, which I mentioned earlier. Linear discriminant analysis can be described through a set of equations, 2 or 3 equations. If sepal length is bigger than 3 and sepal width is smaller than 5, then you are this iris, you know. So that makes the, and in this sense, the nearest neighbor classification is more complicated, you know. All right. In any event, so the nearest neighbor classifier, as I mentioned, has this parameter k, which is the number of nearest neighbors. And if you set k equal to 1, then these boundaries become very non-linear, you know, which gives you a lot of flexibility. However, if you have many nearest neighbors, k equal to 50, then the boundaries start to look almost like hyperplanes, you know. And to choose this parameter k, we can use something called cross-validation. There's a way to decide on the optimal parameter. All right, let me now come to another very famous prediction approach. Or let me stop here and ask, do you have any questions at this point? Okay. Let me come to another prediction algorithm, which is called tree prediction. It has many names, classification trees, recursive partitioning, and so on. So let me come up with an example. Imagine you work in an emergency room and you need an algorithm that predicts who is at a high risk of a heart attack, you know. So somebody comes into the emergency room and says, oh, I have chest pain. And you have to make a decision. Well, does this person have a heart attack? Then you need to drop everything else and immediately attend to them. Or they just have a mild cough or something, you know, and feel anxious. So let's assume that we have a training data set comprised of 250 people, and the outcome variable is high or low risk. And also there are 19 non-invasive clinical and lab variables. So let's start out with the data. So in this data set, actually only 17% of subjects turned out to be high-risk subjects, you know. 83 really didn't require immediate attention. Now, what you can then ask is, well, for a subject, is their blood pressure less than 91? If their blood pressure is less than 91, then you immediately classify them as a high risk. Yeah.
Sorry, I missed. How do you do the first classification? How do you know?
Oh, the algorithm tells you. So the algorithm chooses the. Yeah. There's an algorithm. What's that? Yeah.
Based on the measurement.
Yes. Oh no. Sorry. Well, in your learning data set, somebody, a specialist, reviewed these cases and said, you know, yeah, this was in certain ways their final outcome. This is assumed to be perfect. You know? Okay. Is that what you're asking? Yeah. Yeah. So let's say after a day after these people were treated, somebody reviewed their charts and said, you know what, they actually were a high-risk person. You know. Yes. And anyways, so the tree construction algorithm looked at these 19 non-invasive variables, and in an automatic fashion decided that the best splitting variable is blood pressure. You start out with that. And you say, well, if the blood pressure is less than 91, then 70% of these people turned out to be high risk. So what does that tell you? You don't need to measure anything else. If they have, you classify them as high risk. However, this note requires further attention. So then you ask, is their age less than 62? If yes, they are at a low risk, right? So you see the flow, right? So this person has a low blood pressure and they have a low age. They are not at risk. They may feel anxiety or something else, you know. So no worries here. However, for this group that are older than 62, you measure another variable called ST, and if it is present, you classify them as a high risk, whereas if it's not present, low risk, you know. Now you notice how this classification tree is very intuitive. It's really a flow, a workflow almost. And because it's so intuitive and easily implemented, clinical doctors love it. You know, they love to have simple thresholds. Clinicians love thresholds. Blood pressure less than 90. Okay, I can deal with that. You know. But what's the drawback? It turns out that classification trees are fairly inaccurate as predictors. You know, and so therefore additional improvements are needed to make them more accurate. You know. So this classification tree construction involves several aspects. One is, notice there was always a binary split, blood pressure less than or higher than, you know. Now, people, of course, explored other options, you know, and there have been decades of research of how to form classification trees in an optimal fashion. So don't reinvent the wheel, but if you want to improve it. But in any event, so there's this binary splitting. Then recursive refers to the fact that each daughter node is then split again. You know, so it's in a recursive fashion. So and as I mentioned, the classification trees can be visualized in the Euclidean plane through cuts along the x-axis, you know. So imagine we have a classification tree based on two genes, gene J and gene H, and so then you would, the gene J is on the x-axis and you partition it, and the partitioning really amounts to asking, well, is the gene higher than the threshold or lower? And so you get a a vertical line. And similarly for gene H, you get a vertical line, you know. Now, you already notice that this seems unbiological, you know. Why should there be straight lines along the axes, you know? And that gives you already a glimpse why these methods are not that accurate, you know. But again, these thresholds are things that clinicians love a lot because it simplifies the decision algorithm for them. You know. It turns out that classification trees applied to gene expression data show poor performance. I don't know anyone who uses these methods for gene expression data. So here is the tree or classification tree applied to the iris example, and you notice again these divisions along the axes. There are many other classifiers. a very famous approach is called support vector machines. The computer scientists are probably very familiar with these techniques. Other classifiers are neural networks, random forests, and random generalized linear model. And so I will talk about these methods because they are very good for gene expression data. Another thing I should briefly mention is this aspect of feature selection, in our case, gene selection. So the tree predictor does it automatically. You know, let's say you start with 50,000 genes, the tree would pick the best gene and then find the optimal threshold for it. You know. However, for discriminant analysis and nearest neighbor predictors, you need to pre-select the features. You know, you can't just apply LDA or K nearest neighbor predictors to 50,000 genes. Instead, you would want to use, for example, a t-test and find the 100 genes that are most differentially expressed between high risk and low risk subjects, you know, and then you would apply these methods to these 100 genes only. Now, when you do feature selection as part of the prediction algorithm, then you need to, of course, account for it when you later estimate the prediction accuracy, and we'll get to that. So how do we estimate the prediction error rate, or what is the error rate? Well, the error rate is, of course, just the proportion of observations where the predicted outcome is unequal to the observed outcome, where you got it wrong. Now, there are different types of error rates. There's the so-called test set error rate, and that is calculated by having a second independent data set available, you know. For example, a new data set of 100 cancer subjects. Now, and this is the type of error rate that people want to see when they read a paper. You know, they want to see, well, what was the error rate on a totally independent data set. The other error rate that people report is the learning set error rate, also known as resubstitution error. So what is that? Remember, you started out with a data set, the learning data, or also known as training data, where these are the data you used for building or constructing the predictor. And what you can do, of course, is you can then apply your predictor on the very same data and then make predictions and calculate the error rate. But this error rate will, in general, be highly biased, right? Because you optimize the predictor so that it would perform well on the learning data. The most extreme example is a k-nearest neighbor predictor with k equal to 1. If you apply it to the learning data, you get a perfect accuracy, right? Because you look up each observation and say, what was your outcome? Oh, okay, that will be your predicted outcome, you know. So in any event, that's why the learning set error really has little meaning, except if it is bad, you know. Because if you have a predictor that has a bad error, meaning a high error in the learning data, then you're really doomed, because the predictor will certainly not work on test data, you know. All right. Now another famous term is cross-validation error. So I'll come to it later, but this is an idea of arriving at an unbiased estimate of the error rate in the learning data. And then there's other techniques called bootstrap error rates, but I will not discuss them. So as I mentioned, the resubstitution error rate is estimated using the learning set, and the problem is it has a downward bias. It's overly optimistic. In contrast, the test set error rate is unbiased. And how do we get it? Well, to estimate, let's say you have a very large data set, 200 subjects. What you could do is you could randomly divide these subjects into two data sets. The first set you refer to as learning set, and you build your predictor on the learning data. And the second data set you call the test set. And then you evaluate your predictor on that second data set. Now, that would literally arrive at an unbiased estimate of the error rate. But of course, the problem is that you have a reduced sample size, effective sample size, because you only used 100 subjects for training your predictor. So therefore, people have invented this approach called cross-validation. And let me explain that. So the precise term is V-fold cross-validation, where V is an integer. So for example, 10-fold cross-validation. Assume again we have a data set of 100 subjects, and we want to estimate the 10-fold cross-validation as error rate. So what would we do? We would take these 100 subjects and randomly put them into 10 bins. Why? Because it's 10-fold cross-validation. So each bin would contain 10 human subjects. And then we would do the following. We would take 9 of the bins and build a predictor on these 90 subjects. And then we would evaluate the predictor on the left out bin of 10 subjects, get an error rate. Now that's one way, but now you cycle through the different bins. Now you take out the next bin, and you again have 90 subjects for training a predictor, and again apply it to the left out bin. And so you cycle through each bin. Each bin serves once as a test set. And so you actually end up with 10 different estimates of the error rate, one for each bin. And then you just average them. And that's the V-fold cross-validation error. Okay. Finally, I mentioned there's another error rate called out-of-bag error. And this is a phenomenal way of estimating an error if you deal with something called a bagged predictor. And right now you may be unfamiliar with this term, bagged predictor, but the good thing is I'll teach it to you in a minute or so. All right. So let's come to bad mistakes that a data analyst can do. So it's a common mistake to first do feature selection on all the data and then do cross-validation and model building using these pre-selected features. What do I mean? Imagine you apply linear discriminant analysis to a data set. And let's say, again, you have your 100 subjects, and 50 of them are high-risk cancer patients, 50 are low-risk cancer patients. And what you do is you find 200 genes that are highly differentially expressed between these two groups. Then you use these 200 genes as input of linear discriminant analysis, and you construct your model or predictor. And then you say, you know what? I need to come up with an estimate of the error rate. Well, you say, oh, you know, cross-validation is a good idea. So then you use this 10-fold cross-validation and you arrive at an error rate. And what you will find is that this error rate is phenomenal. Why? Because you used all data to select your genes, you know. What would have been the right way to do it? Coming to cross-validation, 10-fold cross-validation. Imagine you have your 90 subjects that are part of the training data, then only using these 90 subjects, only using them, you find 200 genes that are differentially expressed. Then you use these 200 genes with linear discriminant analysis to come up with a predictor, you know. Now, as you cycle through the bins, when you have the next bin, you have another 90 subjects. Again, you apply your t-test to find 200 differentially expressed genes using these 90 subjects only, okay? So you never use the test data in the feature selection step. That's a critical thing. Let me come up with another terminology that is very useful, which is called the naive predictor. So let's just, do you remember in the example of the emergency room, the vast majority of subjects were low-risk subjects, okay? And so the naive predictor would just say, oh, you know what? Everyone is low risk, you know? And this naive predictor would have an error rate. Do you remember? Let's look at the plot that we had. If you call everyone a low-risk subject, then your error rate is actually only 17%, you know, which seems really low, you know, just 17%. So the naive predictor assigns the same outcome to every subject. And why do we even look at it? Because it turns out that in genomic applications, the naive predictor may be better than any other predictor that you developed, you know. So it may be better than linear discriminant analysis. It may be better than K-nearest neighbor predictor. It may be better than support vector machines. You would be shocked how often that happens, you know. And so, of course, we want to know about it, because if the naive predictor is better than your genomic predictor, why bother spending money on measuring gene expression data? You don't need them, you know. All right, let me come to another topic which I referred to earlier, which is bagging and aggregating classifiers. So let me start out by reminding you that classification tree predictors are terrible predictors, right? And but people, as for example, Leo Brayman, noticed that when you use hundreds of tree predictors together and let these hundreds of trees vote on an outcome, you arrive at a very accurate predictor. And this accurate predictor is known as the random forest predictor, you know. But before we get there, let me maybe review some terminology. So the idea of these aggregated classifiers, also known as ensemble classifiers, is to have multiple weak predictors really on slightly perturbed versions of the data set, you know. So imagine you have your initial 100 subjects. These are your learning data. What you do is you generate new data sets from this original set of 100 subjects. Let's say 500 new data sets. And then you fit a predictor on each of these 500 data sets, and so you arrive at 500 predictors, right? For example, 500 tree predictors. And then you let each of these tree predictors cast a vote, you know, for an outcome. And let's say out of these 500 predictors, 80% of them predict this is a high-risk subject. Then you say this is a high-risk subject. So one famous approach for finding an aggregated predictor is bagging. Bagging is a short term for bootstrap aggregation. And let me review what we mean by the so-called non-parametric bootstrap, you know. So assume that we started out with our 100 subjects, and we want to get a new data set from these 100 subjects. How do we do that? Well, we could just randomly select subjects, but with replacement, you know. So what you start out, you select one, put it in a bag, select another person, put it in a bag, but you always return the subjects. So what you then get is a so-called bootstrap data set, which again contains 100 observations, but now it could have the same, it could have selected the same subject several times, you know. In other words, in your bootstrap data set, John may show up 3 times, randomly chosen 3 times, whereas other subjects were never chosen, you know. Do you get that? Yeah. So there are some observations that are not part of your bootstrap data set. They're not part of your bag. They are out of bag observations. All right. And this seems like a crazy approach to generate new data sets, right? But you can generate one bootstrap data set that of 100 subjects, then another bootstrap data set of 100 subjects, and so on. 500 different bootstrap data sets. And on each bootstrap data set, you can train a tree predictor or any other predictor, right? And then arrive at a vote. One major advantage of bag predictors is that they allow us to estimate so-called the out-of-bag error rate, which is nearly unbiased. And the idea is very intuitive. Well, given that there's actually about a third of subjects will not be part of a particular bootstrapped data set, and you just use these left out cases from each bootstrap sample as a test set, right? And then you classify these out-of-bag cases and compare their predicted outcomes with the true outcome to arrive at an error rate estimate. And that's called out-of-bag estimate of the error rate. So in case of these bag predictors, we don't need cross-validation. It serves no purpose. So as I alluded to, probably the most famous bagged ensemble predictor or aggregated predictor is the random forest predictor. And this is really what I call state-of-the-art predictor, meaning it is arguably one of the best predictors, you know, out there. And so it was developed by Leo Brayman, and it's called random forest because it is based on tree predictors. So instead of looking at one tree, we get a forest comprised of individual classification trees. So the random forest predictor is based on individual trees, but notice there's another adjective, random, right? There's an element of randomness. And before we get there, let me mention that prediction of the random forest is according to plurality voting. So if you have n trees, for example, 500 trees, then you let each tree vote for a particular class, meaning high risk or low risk, for example. And then you just say, well, whatever, it's like in democracy, whoever gets the most votes, that's your final outcome, high risk, for example. Another technique that I just want to mention in one slide is boosting. So that is another very famous algorithm for arriving at an ensemble predictor or aggregated predictor, which has a similar intuition to bagging, but now you don't use the non-parametric bootstrap for creating data sets, but rather you sample data sets, quote unquote, adaptively by increasing the weight for those cases that are often misclassified. I just refer you to the literature. All right, so I taught you a lot of prediction methods, and several papers have evaluated them. One of the first papers to evaluate these predictors in the realm of gene expression data was written by Dudois, Friedland, and Speed. And they evaluated this linear discriminant analysis, diagonal linear discriminant analysis, nearest neighbor predictors, classification trees, bagging, and boosting. Remember, I taught you several prediction methods. And of course, we want to know how well do they perform in practice. And as I mentioned, there is one early publication from 2002 where Dudois et al. Empirically evaluated different predictors on 3 different data sets: the leukemia dataset, lymphoma dataset, and NCI-60 dataset. And now these were all very famous data sets, and so it was very interesting to study them. But just to caution you, these are only 3 different data sets, okay? But in any event, then these authors, Dudois et al., they calculated test set errors for discriminant analysis, classification trees, and so on. And the y-axis shows always the test set errors, and the x-axis shows different methods. And they did this, of course, for the leukemia, lymphoma data, and so on. And so what did they find? It turned out that nearest neighbor predictors and this diagonal linear discriminant analysis had the smallest error rates, okay? And the results really didn't change much with respect to the number of genes that were selected. Remember, for nearest neighbor analysis and discriminant analysis, you need to pre-select the genes. So even if you used, say, 200 genes, it didn't greatly affect the performance. All right. As I mentioned, a major pitfall of this analysis is that it only involved 3 data sets. And it gets worse, because the very first data set, which is a very famous data set involving leukemia, turned out to be extremely unrepresentative of certainly cancers, you know. Why? Because the leukemia data allowed prediction methods to arrive at a very low error rate. And the reason was because the classification into B-cell ALL, T-cell ALL, and AML could be accomplished because these tumor classes are extremely distinct. And so, unfortunately, these early successes misled many of us, you know, to think that, oh wow, we can really classify cancers very well, you know. And that just didn't turn out to be true. The other thing is the NCI-60 dataset was also very unrepresentative. Why? Because it had 8 different classes. And in most applications, we don't have 8 different classes. We may have 2 or 3 classes. So although this comparison study was very valuable at the time, it really involved data sets that are not what we encounter in practice. And so then another group of authors studied more cancer data sets, so leukemia, breast, brain, colon, and so on. And they also reported different error rates for support vector machines, k-nearest neighbor predictors, diagonal linear discriminant analysis. A method I didn't talk about is shrunken centroid predictors, nearest neural networks, and the random forest. And when we looked at these error rates, we learned that often these simple predictors, DLDA, KNN, work similar to complex predictors. What is a complex predictor? The random forest would be a very complex predictor because it's an ensemble predictor. And even this analysis is limited in the fact that it involves few data sets. And so then I had a graduate student who wanted to do research in supervised machine learning. And so I told her to analyze hundreds and hundreds of data sets. And I will show you the results of that comparison shortly, But before we get there, let me mention now another prediction method that was just published in 2013. Remember how I promised you to take you from the 1930s to the current date? And I present it because this is probably the most accurate prediction method I know for gene expression data. And let me review very briefly what is meant by a generalized linear model. Of course, all of you know linear models, right? So you have often you assume a normally distributed outcome like a Gaussian, and then you have a simple regression model. Many of you also know logistic regression, right, where you have a binary outcome. But there are also other methods called Poisson regression and multinomial models and so on. And all of these models can be summarized in a whole class of models, which is called generalized linear models. And so the predictor that I will describe is essentially creates an ensemble of generalized linear models. Now, although generalized linear models typically are not related to survival outcomes, for the experts I mentioned, if you have a survival outcome, cancer survival time, which is a censored variable, this predictor can also deal with that. I mean, this random GLM predictor can really be applied to most outcome types you can think of. Count outcomes, categorical outcomes, quantitative outcomes, and so on. So I already mentioned to you many of these alternative approaches that have been developed. For example, just plain old generalized linear models, just logistic regression would be one predictor. Another famous approach is based on penalized regression models. So the generalized linear model predictor is an ensemble predictor where each individual predictor is a generalized linear model. For example, if you have a binary outcome, then it would be an ensemble of logistic regression models. So how did we even find this predictor? Because when Lin Song started her research, I said, before you do anything, I would like a very careful and comprehensive empirical evaluation of all the prediction models out there. And so what we needed was to have hundreds of data sets available. And how did we arrive there? So let me teach you a trick. So let's say you have a single gene expression data set. What can you do? Well, you can take one of the genes and consider its expression values as an outcome, right? And what you can do is you can dichotomize this outcome, for example, by the median value. You say high expression versus low expression. And what you can do is you can then take the remaining genes as covariates or as features to predict the expression levels of this particular gene. It seems artificial, but this type of analysis can be clinically very interesting, because let's say you want to know creatinine levels or HDL levels, they are often highly related to gene expression levels. And so this dichotomized gene expression trait can be quite meaningful. So in any event, for each data set, you can of course go look at multiple gene traits. And so what Lynn did, she went to each individual microarray data set and chose 100 gene traits in a random fashion. Each gene trait was dichotomized, and then we arrived at 100 different outcomes per gene expression data sets. And so then we had 7 different data sets, and so therefore we ended up with 700 comparisons for these predictors. But apart from using these data sets, there's also a collection of so-called machine learning benchmark data sets. The machine learning community has long recognized the need for having a collection of empirical data for evaluating prediction methods. And so there's something called the UC Irvine machine learning benchmark data sets. And so there are about 20 of them. And so one can also evaluate predictors on these data sets. And so we also evaluated it there. Okay, back to reality. So here we are. I mentioned these approaches that were used in the comparison. So they also support vector machine. There's a technique, shrunken centroids, which is a very accurate predictor proposed by Tibshirani et al. And all right, I already taught you bagging, which is bootstrap aggregating a predictor. And that's, of course, the first thing you could do. When you have a logistic regression model, you could say, well, why don't I bag it to get at 500 logistic regression models? And you may hope that this leads to a more accurate predictor. But it turns out that's not the case. There's a reason why people don't bag logistic regression models, because it's not worth it, you know. Now, the rationale behind the random generalized linear model predictor is the following. It really combines the advantages of 2 different types of approaches. The first approach is the random forest predictor. Its main selling point is, of course, its incredible accuracy. It's a highly accurate predictor. But what is the drawback of this predictor? It's hard to interpret. Why? Because you have 500 different tree predictors. Each tree predictor has a lot of partitions. Nasty, you know. That's why they call it a black box predictor. It's highly accurate, but you just don't know why, you know. Now, let's contrast that to something that epidemiologists love to do, forward variable selection. You know, let's say you have a logistic regression model or a linear regression model. You may be familiar with stepwise variable selection. So you would, for example, start out selecting the one gene that shows the strongest relationship to your outcome. Then you say, well, what can I add a second gene to it to make the resulting predictor even more accurate, or a third one, or a fourth one? And so this stepwise, or this forward variable selection then leads to a predictor that is easy to interpret. Why? Because it may involve only 3 or 4 genes. But of course, the problem is that forward regression overfits the data, and you end up with a predictor that is very inaccurate. Now, the random GLM predictor combines the advantages of both of these approaches. On the one hand, it gets an accuracy that is as good as, if not better than that of the random forest. But also, it typically involves surprisingly few variables, think 20 or so. And so it's much more interpretable. So let me describe this approach. As I mentioned, RGLM is an ensemble predictor based on bootstrap aggregation of individual generalized linear models. And the covariates of each model are selected using forward regression according to this AIC criterion. And the RGLM, or the random GLM, combines 2 seemingly wrong choices for changing a GLM. So the first thing is, let's say you have GLM logistic regression. Just to be clear, logistic regression is a phenomenal predictor. We love it, everyone uses it, it's well known to be a very good model. And as I mentioned, you could say, well, why don't I bag it? But this is typically unnecessary, and if anything, it makes things worse. And why? Because logistic regression is very stable. When you have a stable predictor, then bagging doesn't help. The other thing one can do with GLM is you can do forward variable selection. And of course, the great advantage is interpretability. You end up with 3 or 4 variables maybe, but it is a bad idea because you get poor accuracy due to overfitting. Now the random GLM actually combines these 2 wrong choices and actually then leads to excellent prediction accuracy and inherits some of the interpretability from forward selection. Let me describe it to you how it works. So let's assume we start out with 100 cancer subjects and let's say 10,000 genes. So the first thing, the first step is to arrive at bootstrap data sets by sampling with replacement. So let's say you end up with 100 bootstrap data sets. Now each data set has, of course, these 100 subjects, and each data set involves 10,000 genes. So then what you do is you take a random subset of the genes for each bag, okay? So you start out with 10,000 genes and you randomly select only 3,000 of the genes. Sounds crazy, but that's why it's called random, because you randomly choose these genes. The next thing you do is you need to decide, do I want to have pairwise interaction terms between these genes, yes or no? But let's say no. Then you do the next thing. Out of these 3,000 genes, you select, for example, the 50 genes that have the highest relationship with your outcome. For example, the highest correlation with your outcome. And then you use these 50 genes as starting point of forward variable selection. Okay, you use then the generalized linear model based on these 50 variables, and the algorithm chooses, let's say, 4 or 5 out of these genes. So you end up then with one generalized linear model for each of these bootstrap data sets. And so it's really a multivariate logistic model. And then you just aggregate their predictions into a final prediction, you know. Now, we evaluated this method on many data sets. So one is these 20 cancer data sets and disease-related data sets. Also these 700 dichotomized gene trait data sets that I mentioned. Also on 12 UCI benchmark data sets, and then on 180 simulations. And so we did that for the binary outcomes, but also for the continuous. So what is the continuous outcome? A continuous outcome is just a numeric number. You know, it could be, for example, HDL levels, or just the gene trait, undichotomized. And what we found is that this random GLM really at least tied for the first place, if it wasn't the first place. So, so it consistently had superior performance. And because of that, I present it to you today, you know. Actually, the way we found this predictor was by evaluating it empirically. You know, you notice that when you look at these this flow chart, all choices are actually fairly reasonable for people who do machine learning, do research in machine learning. But in any event, it is what it is. So let me describe the performance on these 20 cancer-related data sets and disease-related disease-related data sets. So there are adenocarcinoma, brain cancer, breast cancer, but also we have diseases such as psoriasis, multiple sclerosis, and so on. What do we learn here? All of these data sets actually have relatively few human subjects, low sample sizes, and the features, we often restricted it to maybe 5,000 genes or so. And when we then looked at the prediction accuracy of all of these methods in these data sets, here's a long table, but here's the mean accuracy. And this random GLM method really performed very well. It outperformed all other methods. Now, the good news is that actually all methods work fairly well, you know. So look, so the best method has an accuracy of 0.871, but then so that's the random GLM, but if you just compare it to the random forest, it's almost 0.86, you know. So even if you had used the random forest, you will be in good shape. But now look at the this is the tree predictor, and also in R it's called rpart. That has a terrible accuracy. Remember how I kept saying the tree predictors have poor accuracy? Here it is. That's the evidence, you know. Other prediction methods such as k-nearest neighbors, it is what it is. It is less, you know, 0.844. So I would support vector machines perform surprisingly poorly here, you know. So this is probably the largest empirical evaluation on disease data sets, you know, having 20 data sets. But even if you have 20 data sets, that really isn't the same as having 700 data sets, you know. And so let's once and for all settle which method is best by looking at these dichotomized gene traits, where, as I outlined earlier, we started with 7 human and mouse expression data sets and randomly selected 100 gene traits. And here are the box plots of prediction accuracy versus different methods. So it's no surprise the random GLM is the most accurate predictor. And let's compare it again to alternatives. It is slightly better as the random forest predictor. It's much better than the tree predictor. And also, it is much better than just a forward selected GLM, you know. Right? Coming back to the idea, well, if we have a logistic regression model and we apply forward variable selection, which is a very intuitive and sparse predictor, but you really pay for that. It's not as accurate as other approaches, you know. Okay, let's move to these very famous UCI benchmark data sets. And what is known, or what is striking about them is they actually involve many observations, right? Remember earlier we may have had 50 cancer subjects. Now we have hundreds of subjects, you know. And the other thing is they involve few features. In the previous comparison, we had 5,000 genes as covariates. Now we have 9 features, 16 features, and so on. And because we have so few features, it's really recommended to create pairwise interactions between the features. That turns out to be an important idea for the RGLM. This random GLM really is often a superior method when you have a reasonable number of features. And so here is the evaluation on these UCI benchmark data sets. And notice when you have the RGLM without interaction terms, the performance is not great. It ranks 6th. But the minute you allow for interaction terms, it ties with the best performing methods, you know. So what do we learn? The random GLM is not just a superior method for microarray data and high dimensional data. It is also state of the art for lower dimensional data sets. interesting, so it ties with what other methods? The random forest, and it ties with support vector machines, you know. And for people who know the machine learning field, the random forest and support vector machines may be the most famous methods, you know. And why are they famous? Well, because they do perform very well on the benchmark data, you know. And so we replicate it, you know. All right, we of course also evaluated these methods on simulation. So this is the result over 180 simulations. And again, we find the random GLM really, if not ties for first place, it really outperforms many of these other approaches. And then we also applied it to mouse tissue data, and where my colleague Jake Lucis studied physiologic traits, for example, insulin levels, HDL, and so on. Yes?
I'm just curious, did you also allow the other methods to include two-way interaction terms?
Yes, yes. So, absolutely. So, that's a very important question. So, of course, you could say, well, maybe the R part would do better if we also allowed for two-way interactions, or even three-way interactions, you know, or support vector machines would be even better. And so we did the analysis, and it just turned out the other methods got worse. So, you know, why? Because, for example, support vector machine is a nonlinear predictor, or actually, I don't quite know why that is, but it doesn't need that, you know. Similarly, the random forest gets worse if you allow for pairwise interactions, you know. And so it's really only the RGLM benefits from it. Yeah. Okay. Yeah, in any event, so for these mouse tissues, we get a similar story, you know. So now another thing you can do is you can evaluate methods for predicting continuous outcomes, you know, where you don't dichotomize a gene trait, for example. And here, so then the forward GLM is just linear regression, you know. And again, so it outperforms linear regression when you measure accuracy, where accuracy is now measured by correlating the predicted value to the truly observed test set value. That's the measure of accuracy. So that's why we call it prediction correlation. And in simulation studies, the same. Now, so we really like, obviously, the random GLM, but I want to mention one caveat already, which is on large data sets, it could take a couple of hours to calculate, you know. So for these cancer data sets, I mentioned the calculation takes about, 30 seconds or so. But let's say you do have a very large data set comprised of 10,000 subjects, you know. Suddenly you would notice that the calculation could take several hours, you know. And in contrast, there's an approach which is these penalized regression models, for example, Lasso and ElasticNet, they are fast, they're viciously fast, and which makes them very attractive. And yeah, I just mentioned an R package. It's called GLMNet that implements these. And so I like these approaches, but we compared then RGLM to these approaches, penalized regression models, and on all of these data, the 20 disease-related data sets, the dichotomized expression data, the benchmark data, the simulations. And so this table reports differences in accuracy. And so the fact that all of it looks reddish or at least white means it actually did outperform on average the penalized regression models, which to me suggests it really requires additional studies to understand why it really outperforms them, you know. So that was for the binary outcome. It also outperforms these continuous outcomes, you know. So in any event, another topic I want to discuss now is the idea of quote-unquote thinning an ensemble predictor. So what do I mean by that? So the goal of a thinned version of a random generalized linear model is to define a sparse predictor that involves very few features. Okay. Why? Coming back to the idea of interpretability, if you have a predictor based on 10 genes, there's a good chance you can interpret it well. And this idea is based on the observation that in each bag, of course, forward variable selection is used, and it turns out that some features are rarely selected. So let's say you have your random GLM predictor, and it is based on 300 genes, but it could turn out that one of these 300 genes was only selected in one bag. And so you could say, well, do I really need to go through the hassle of measuring the gene? Why can't I just take the remaining 299 genes, And so that's then the idea. Omit the features that are rarely used by these GLMs and refit each GLM per bag without the omitted features. So let's look at that in comparison to the random forest predictor. So if you have a typical application, then the random forest may select 40% of the genes somehow in its construction. When you have your 5,000 or 50,000 probes, roughly half of them will be needed in the random forest, which is why it's a black box predictor. In contrast, already the RGLM only uses 2 to 6% of the genes. Why? Because it uses this variable selection step, several variable selection steps. So by construction, it already involves fewer features. However, when you couple this with the thinning idea, you get even fewer. And so, again, the idea for thinning is to keep tracks of how often a variable was selected for the GLMs. And so there's a variable called time selected by forward regression, which, guess what it measures? It measures how often a variable was selected in the final forward regression model. And then, of course, the idea is to develop a thinning threshold where you say only variables that were selected at least 3 times, only those should be used. And you can study how the prediction accuracy depends on this thinning threshold. And so let's say you have a thinning threshold of 2 or 3 or 4. Notice the accuracy is barely affected, which is intuitive, right? If a gene was only selected once, it really doesn't have much of an influence. However, if you have a thinning threshold of maybe 5, you suddenly end up with a drastic drop in the number of genes involved. So this is the average percent of genes left for the prediction for different thinning thresholds, and you notice it really goes down a lot. And so here I show you when you have a thinning threshold of 20, while the RGLM may have involved, 180 genes, suddenly you're down to a handful of genes, So RGLM pros and cons. Pros, astonishing accuracy. It often outperforms existing methods. And the other pro is few features contribute to the prediction, especially if you use this thinning idea. It's also easily interpretable since it involves relatively few features, and it provides very useful byproducts. For example, these out-of-bag estimates of the prediction accuracy. When you apply this predictor, you don't need to do cross-validation to estimate the accuracy. You can automatically use the out-of-bag estimate. The GLM formulation allows you to fit different types of outcomes: binary outcomes, quantitative outcomes, count outcomes, multi-class outcomes, and survival outcomes. Another very noteworthy advantage, which I didn't mention, is the following. It allows you to force particular variables into the model, you know. And so, so we call these mandatory covariates. What do I mean by that? Imagine you want to predict lung disease. There's something called COPD, chronic pulmonary disease, you know, obstructive pulmonary disease, you know. And actually there was a data analysis competition called the Improver Challenge, where the organizers really had these microarray data on COPD, and they wanted that different teams use the data to predict then disease status. And it turned out we participated in this competition and we won it. And but I mention it because why did we win this competition, you know? Well, the reason is because we recognized that it really matters whether somebody smokes and how old they are when it comes to lung disease, right? It sounds like a stupid statement, but it really matters, you know. People who are smokers are more likely to have lung disease, you know. And because of that insight, we realized that when we construct each of these individual GLM models, we want to force smoking status into each of these GLMs. Any epidemiologist would immediately do it in a logistic model. They would, of course, force these important variables into the model. And so our GLM has an argument where you say these variables are mandatory. They should be used in every single bag as covariates. And because of that, by forcing it in, our RGLM predictor outperformed naturally predictors that didn't hone in on these key variables, you know. Contrasted to the random forest. The random forest predictor, as the name indicates, actually randomly selects a subset of variables and just by, on average, rarely selected smoking status, you know. And therefore, yeah, so you get a sense how important it can be to have this option to force mandatory covariates into a predictor. All right, the big con in the RGLM is that it can be slower than common predictors if you have very large data sets. And now the good news is in our R implementation, we have an option that allows you to parallelize the calculation. And so I'll show that to you shortly. Yeah.
I'm just curious, why do you choose AIC other than BIC?
I think it just worked better. I think I'm not 100% sure that we used also BIC, but I really hope we did, you know. So at some point, we researched different ways of doing variable selection. As a matter of fact, we also studied what if you use, for example, a penalized regression model, right? In each bag, you use a penalized regression model, such as ElasticNet or Lasso, which would have been very attractive to me. Theoretically, it would have been very attractive, but it just turned out that this is a bad idea when it wasn't as good as the AIC. Yes?
Sorry, this is maybe a question, but I'm having a little bit of trouble with this idea of random selection, because so how do you make sure that you get reproducible results? If you randomly select a set of genes to create a classifier that you do it again, you're going to get a different list. Right?
Yes. Yes. Yeah. Okay. Just to repeat the question, why do we inject these elements of randomness? There are actually several elements. So one, the main element would be we start out with 10,000 genes and we randomly select, for example, 3,000 genes out of this original set. And the other element of randomness is certainly bagging, right? Because we randomly select a set of subject for each bootstrap data set. And it turns out that injecting these elements of randomness is absolutely crucial to improve the accuracy of the prediction method. There are theoretical papers that show it, that when you have this randomness, in certain ways, it perturbs the data, and it leads to higher accuracy. So why is that? You know, it's actually a good question. There are several arguments why it's a good idea. You know, fundamentally, it allows you to get around. It in certain ways robustifies your analysis. You know, if you have one data set, it could then the resulting prediction could really be driven by some of the data points, and they may mislead you. But by injecting randomness, you move away from that, you know, and you may therefore capture different aspects. Sorry, I'm a bit hand-wavy because it really requires actually a more detailed analysis. But I should tell you that the result is not that random, because you may use, for example, 200 or 500 GLMs. And so after a while, the randomness averages out, you know. That's the beauty of statistics, of the law of large numbers, right? I mean, you have hundreds of GLMs, and you average their prediction. It becomes very robust, you know. And also, of course, in R, you save all of this as an R object. And as a matter of fact, so the function outputs the generalized linear model for each bag. So you have a data frame where each column reports the coefficient values of the logistic models. And so it's highly reproducible and publishable, you know. Yeah, other questions? Yeah. Mm-hmm. Okay, you know, okay, so penalized regression models penalize for the selection of many variables, you know. So let's start out with another approach, forward regression, you know. So let's say you add more and more variables, then you can show that if you look at the training set accuracy, the more variables you add, the more accurate it gets, you know. So what you need to do is you need to penalize for the fact that you add more and more variables, you know. And so the penalization term can take different shapes depending on what penalization method you use. The lasso method has a different penalization term from the ridge regression, from elastic net, and so on, you know. It's really a very interesting subject. I urge you to do a Google search on that. Yes?
I'm wondering if the few features trained with this method is kind of specific to biology. Like, is this one always scoring well in these biological data sets because that's kind of how the biology works? Or, so if you take this method and do it on physics or something else, does it work poorly?
No, it would go very well. And you know why I know? It's because the UCI benchmark data, they are not biological data sets. You know, they involve data sets from physics and all sorts of arenas. These data sets were collected from computer scientists, you know, that apply their machine learning methods to a wide range of topics, you know. So no, I think this random GLM should be explored in other realms as well, you know. Mm-hmm. Yes? Yes.
Estimate parameters and then just basically fit a model of that and then just generate Monte Carlo samples. And then if you do that, have you done that? I guess.
No, I haven't done it. Yeah. So here, of course, I highlight what is known as non-parametric bootstrap method. But I briefly mentioned there are other ways of getting new data sets. A famous one is boosting. But as you mentioned, of course, there's also vast literature on using Monte Carlo methods and Bayesian methods, you know. The idea is often to just create somehow an ensemble of predictions and then average it in some shape and form. And usually, this is a very good idea when you have what is known as a weak learner, meaning an individual prediction method that is unstable. Prime example are tree predictors. They are actually very unstable. You know, if a change in the data set may result in different splitting groups, drastically different splitting groups, highly unstable method. But by using these unstable methods as input of an ensemble predictor, you often gain great accuracy. And just to come back to an earlier question, why inject these elements of randomness, right? Why, the answer is that we want that the resulting individual predictors are unstable. That's really the critical thing. Because if you start with stable methods, for example, logistic regression is a linear predictor in essence, it's highly stable, then creating an aggregated version of it, as I mentioned, actually is a bad idea and makes things worse, you know. And therefore, it was critical to inject some sort of randomness in the logistic model, which we accomplished in these two ways, you know. Yeah. Yes?
You're talking here about features being general features that we're not really talking about characteristics of features, but I know that some of these machine learning algorithms are kind of sensitive to particularly differences or correlations between features. So,
yes.
For example, categorical features versus continuous features can be chosen with different rates, for example.
Yes. That's true. That's particularly true for the random forest also. Yeah, exactly.
Random forest is actually what I'm talking about.
Yeah, exactly.
Any of those caveats carry over to random GLMs?
I'm not sure. I haven't really carefully looked at that, you know. I can only say that I guess I would refer you to the benchmark data to the extent that they have a mixture of different types of variables, categorical and numeric, you know. One could look at that, you know. Mm-hmm. All right. Let me continue briefly and mention there's an R software implementation of the Random GLM. I want to recommend that you check it out. Other things I mentioned is when you do have low dimensional data, think like 10 variables or so, or 5 variables, you want to specify that there are interaction terms, and that's easily done. There's an option where you say, I want pairwise interactions. I want interactions comprised of 3 terms. But we actually have never found that 3-way interactions are better than 2-way interactions. Not a single data set where it worked better. And also, I mentioned that the algorithm outputs this variable importance measure, which is times selected by forward regression. And we use it, of course, to arrive at a thinned predictor. There's an R function that automatically thins your predictor, you know. But you could also use that variable importance measure to select genes if you care to do that. Oops. So now what I will do is I will give you an R tutorial. For example, let me start out with a Word document which is called mini tutorial for the Random GLM package. And so here there's an R library that you can install. And I mean, just to give you a sense, as you know, R is hopefully installed on your desktop. And so now the way we interact with these R tutorials, which you can find on our webpage, is by copying and pasting. That's what I do, so I copy and paste things. from the Word document. And there's a data set called Mini, for Mini data set, for the Mini tutorial, really. And it's actually a brain cancer data set. And so then you can also specify learning data and test data. And notice these are the sample sizes. Your test data set contained 33 of class 0 and 32 of class 1. And then the random GLM predictor is invoked by this R command. There's a random GLM function. And what you do is you specify what are the training data, what is the training set outcome. And here you can specify a test data set, an independent data set. And what you tell the function is, well, is it classification or not? Meaning, is it remember the outcome is 0, 1. So it could be a numeric trait, but you want to tell it, no, it's a class outcome. And n threads refers to parallelization. You can say my computer has, 8 cores, and so you could specify more threads here to speed things up. And when you do that, you then get the predicted value, which is the out-of-bag prediction in the training data. Remember how I mentioned to you, you don't need to do cross-validation because you have these out-of-bag predictions. And what we learn here is then we can relate the out-of-bag predictions to the true outcomes. And what we see is that the accuracy is actually fairly good, right? You notice there's only 4 and 6 subjects get misclassified, But also, of course, you can arrive at a test set prediction. So when I ran this RGLM command, random GLM, I saved the output of that function into an object, which I call RGLM. That's an R object. And so the R object has several components. For example, and you get the components using the $sign. Do you remember? It's a list component. You say, give me the predicted test set outcome. And when we do it, we see, again, it's actually quite accurate, this predictor in this example, Now, one attractive thing about the RGLM is that it actually gives you probabilities, Remember, even a logistic regression model allows you to get probabilities for the different classes. And so, and you get that here too. You can say, I want these class probabilities. And here it is. So for this one particular human subject, the probability that they are class 1 is about 57.9%, and so on. So you get probabilities. So you could threshold these probabilities. And also to get the variable importance measure, you use the list component called time selected by forward regression. And then you can ask, well, how often was each feature selected? So for example, this particular gene was selected 10 times, And then you can say, well, which are the 20 most important features? And it turns out these genes are the most important features, for example, and here's the count, how often they were selected, To fit a quantitative outcome, you really use a very similar command. Let's see, here it is, X, Y, and so on, and I just say classify equals to false, And so again, I get these outcomes, Now, there are additional tutorials on the random GLM at these web pages. For example, there's one tutorial which shows you how to tune parameters. The random GLM does involve parameters. And the default choices work very well. If you're lazy about it, you do nothing, But there is a way to use the out-of-bag estimates of the accuracy in your training data to fine-tune parameters and to further improve the performance of the predictor. And the other tutorial I mentioned, there's a tutorial that shows you how to interpret the RGLM predictor. So let's say you have your RGLM, there's a way to reduce, let's say, 100 or 200 logistic regression models, individual logistic regression models, into one overall logistic regression model, which then allows you to come up at a nice interpretation. And there are also ways to visualize the model and so on. All right. There's another tutorial. Do you still have strength to see some additional tutorial, or you need a break? Who needs a break? Okay, good. Let me just briefly mention it, because it's a unit. So on the web page, we also post a second tutorial, which is called Prediction of Simulated Expression Data. And that presents R code for the other predictors I mentioned, right? I just talked about Random GLM, but now remember I mentioned linear discriminant analysis, k-nearest neighbor predictor, support random forest, and so on. And so later tonight, you could just try to read these libraries into your R session. For example, the R-part library for tree predictors and so on. And then here I have some code for generating gene expression data. It's actually very nice R code for simulating gene expression data. And I simulate two data sets, a training set and a test set. And the data sets are called DUT expression, for example, for the training set, and DUT expression test. And I use a convention that I want to highlight already. When I call a data set DUT expression, it always means that the genes are the columns, okay? Which is different from what other people do. But you will appreciate that convention if you, as you go along. Yeah? And so notice, when I say the dimension of DUT expression, there's 100 human subjects and 3,000 genes, So why do I follow this convention? Because pretty much all R functions assume that the variables correspond to columns. And when we predict anything, what we predict it based on genes. These are the variables. So it's natural to go through the effort to turn your data into this format, because everything else you do downstream will become far easier. So in any event, so we have the simulated expression data. We also have a simulated outcome, the Y vector. So there are 50 subjects of class 1, 50 of class 2. And the first thing I can do is I can say, well, which genes are most differentially expressed between class 1 and class 2? And to do that, I use a tremendously valuable R function called standard screening binary trait. What does that mean? What is screening? Well, we screen for genes. We want important genes. What does standard mean? Standard, well, it looks at each gene one at a time and calculates a t-test, a fold change, the standard differential expression analysis. And yeah, so I input that. It also outputs Q values if you wanted to, So I hope you have learned of false discovery rate and Q values, and so it also outputs that, In any event, so we can then say, well, give us the top 20 most differentially expressed genes. Why do I care about that? Well, because for linear discriminant analysis and the k-nearest neighbor predictor, I need to input selected genes, So I do that. So then we can fit a tree predictor, and we do that by using the rpart command. And so this is the R command. So we regress the factor outcome on all the selected gene expression values. And this is the tree that you get, you know. Unfortunately, it looks ugly, you know. So what does it tell me? Well, gene number 1472 should be thresholded at 0.24. That's the outcome, you know. All right. And in any event, I want to use the tree to make predictions. And so to do that, I use the predict function. So I remember the tree was saved into an object called RP1. And so I apply then the predict function on RP1, and I say the new data set, actually new data equal dot expression gives us the evaluation on the learning data, right? And so then I can cross-tabulate the training set prediction or learning data set prediction with the observed outcome, and here's what I get. And so I misclassify 3 plus 9 subjects. And so when you calculate the proportion of misclassifications, it is 12%, which is overly optimistic because it's a training set error. Now we can repeat the analysis on the independent test data sets, and I can then cross-tabulate the predicted value versus the test set outcome. And what do I see? Wow, the error rate is 35%, which is much higher, you know, which reflects, well, tree predictors aren't great, you know. To calculate the naive error rate, I can use this code, and, well, never mind. As I mentioned, a really phenomenal predictor is the random forest predictor, and so it's very attractive, and that's why I want to teach you the code. So same logic, you input the gene expression data, you input the outcome, and the random forest has one parameter, which is called mtry. It is the number of randomly selected variables at each node split. I leave it at that. In any event, we say we want the random forest comprised of 500 trees, and then the output of the random forest is attractive because it automatically gives us the out-of-bag estimate of the error rate, which is 38%, you know. And then we can apply it to the test data. Always the same logic. You use the predict function on the object, and you say new data equal, you know. And then we get this error rate, which is already better than that of the tree predictor. Remember, the tree predictor had a test set error of 38%. To fit linear discriminant analysis, you use the command LDA, you know. And so you say factor outcome regressed on these variables. And again, you can calculate the misclassification error and test set error and so on. But yes, as I mentioned, when you calculate a cross-validation error for linear discriminant analysis, you need to account for the fact you need to carry out variable selection in each of the training data separately. And so here I give you some R code which gives you the correct way of calculating a cross-validation error rate for linear discriminant analysis. And I won't go through the details, but it is valuable code for people who like LDA, so I felt I should give you that, you know. K nearest neighbor predictors can be invoked using the KNN command. And see, you say, well, what is K? You could say, I want 3 nearest neighbors, you know. And it turns out that the error rate really does depend on K, you know. So here's a plot, and you see, well, if I choose, what, about 30, K equal to 31, I get the lowest error rate, you know. As I mentioned, we also have, of course, the other option of using the random GLM, so I also apply it here on these data, and then I get a test set error of 27.27, which is quite similar, ever so slightly higher than that of the random forest, you know. Yeah, so the homework is choose top number of genes 50, because I chose 20, you know. Remember, we chose early on the 20 most differentially expressed genes, so you could see what happens if you use 50. And yeah, so that concludes our lecture on supervised learning methods. And then let's take a little break, and then we start the topic of unsupervised methods, meaning hierarchical clustering, you know. So let's take a 5-minute break, you know, and resume it later. Thanks.